The minerals are made up of chemical compounds which consist of anion and cation groups. Accordingly, based on the nature of anionic group present in the minerals, they may be classified into following major divisions or classes. Number 1 is native elements, the second is sulfides, third is oxides and hydroxides, fourth one is halides, fifth one is carbonates, nitrates, borates and iodates, then sixth one is sulfates, chromates, molybdate, tungstates, and seventh one is phosphates and arsenides and vanadates, and finally the eighth group is or eighth class is silicates. There are numerous species belonging to each class. In nature, there are about 5,000 species of minerals, of which 1/3 of the species are represented by silicates. Further, about 95% of the minerals present are rock forming minerals. The silicate comprises the largest chemical group among the minerals. It includes about 1/3 of all mineral species. Although many of these minerals are quite rare, others are make up a large part of Earth's crust. In fact, the crust has been estimated to consist of about 95% of silicate minerals, of which some 60% of feldspars and 12% of quartz. The predominance of silicates and aluminosilicates reflects the abundance of oxygen, silicon and aluminum, which are the most common elements in the Earth's crust. The 8 most common chemical elements in the Earth's crust are as follows. One is oxygen, followed by silica, aluminum, iron and calcium, sodium, potash, magnesium. So, number of elements that form silicate minerals is comparatively few. Some additional elements such as rubidium and strontium do not form a specific silicate minerals. Instead, they are dispersed in small amounts, replacing more abundant elements in several silicate minerals. Still, other elements that do not form a common independent silicates occur associated with other cations, example boron, which forms a number of borosilicates. The great multiplicity of silicate minerals is due to the variety of silicates that can be formed from the same elements. Many have complex and variable compositions, complexities that hindered the development of satisfactory classification of silicate minerals until X-ray investigations provided the means for determining their crystal structure. Silicates are compounds containing anionic and silicon compounds. Terrestrial planets, Earth's crust and asteroids are comprised of silicates. The best example of silicates in daily life are cement, sand and many of the minerals. The variety of silicate minerals is produced by SiO4 tetrahedra linking to a similar units and sharing 1, 2 or 3 or all 4 corner oxygens of the tetrahedron. Quartz and the feldspars are some of the most common framework silicates, and the ratio of silica to oxygen is 1:2. The anionic group in the silicate minerals is represented by SiO and combination of in various ratios, whereas cations that can combine with these radicals are very few. The important cations are Mg, Fe, Ca, Na, Ti and aluminum, etc. Classification of silicate minerals are of 2 types. One is silicic acid classification, structural classification. Silicic acid classification, this is one of the earliest classifications which occur before the formation of a silica tetrahedron. The silicic acid basis had some success in the interpretation of some of the simpler compounds, but it led to manifest when it was applied to most complex minerals. Some of the hypothetical silicic acid as follows. One is orthosilicic acid, metasilicic acid, orthodisilicic acid, trisilicic acid, etc. Structural classifications. This classification came into existence by the investigation of X-ray studies. The silica tetrahedra has a tendency towards the polymerization. This SiO4 tetrahedra polymerization takes place always through common sharing of oxygens. never by sharing of edges or faces of tetrahedral. There are three possible types of edges of faces of tetrahedra polymerization. Phase sharing, the silicate ions are not separated from each other by intervening anions and also very close to each other. There is a strong repulsion between these two highly charged cations that leads to instability of the structure. Second one is edge sharing. The silicate ions are still not separated from each other by intervening oxygen anions, although they are positioned further apart than in the phase sharing examples. There is still a strong repulsion between them and an inherent stability to the structures. Third one is in corner sharing. Silicate ions are separated from each other by an intervening oxygen and they are as far as apart as can possibility be arranged to add even more stability to the structure. The sharing of edges and particularly of faces by the anion polyhedral decreases the stability of anionic crystals structure. In other words, highly charged cations prefer to maintain as large separation as possible within a structure and to have anions intervening between them so as to screen the charges of one from the other. In nearly all silicate structures, the silicon atoms are in four-folded combinations with oxygen. The bonds between the silicon and oxygen are so strong that our 4 oxygens are always at the corners of a tetrahedron of nearly constant dimensions and regular shape. Whatever the configuration of the rest of the silicate structure, classification for most silicate minerals is based on the types of linkages as follows. One is independent tetrahedral groups, that is nesosilicates. The second one is double tetrahedral structures, that is sorosilicates. Ring structures, also called as cyclosilicates. The fourth one is chain structure, that is inosilicates. Then sheet structures or pillosilicates, and finally 3-dimensional network, that is also called as Tac Toe Silicates. Let us discuss one by one. Independent tetrahedral group, this is nothing but a nesosilicates. In this class, the silicon oxygen tetrahedra are present as separate entities. The resultant composition is SiO4, which gives such minerals as foresterite, that is Mg2SiO4. This division of silicate with this silica is to oxygen ratio is 1:4 is known as nesosilicates. Nesosilicates are those silicates with isolated SiO4 groups in the structure. Under the absolute silicic acid theory, they were considered to be salt of orthosilicic acid, that is H4SiO4, and called orthosilicates. It is noteworthy that in the nesosilicates, aluminum seldom substitute for silica. So, their formula generally correspond to strictly to SiO4 or a multiple thereof. Another feature of the nesosilicate is the absence of compounds with the alkali elements. The nesosilicates have notably dense atomic packing and their physical properties reflect this. They are relatively ordered and with exceptions have higher density than corresponding compounds of the other silicate structures. The absence of chains and sheets is reflected in the generally equidimensional nature of the crystals. Let us go to the second classification, that is double tetrahedral structures, thus also called as sorosilicates. Two silicon oxygen tetrahedra are linked by the sharing of one oxygen between them. The resulting composition is Si2O7 with Si:0 ratio of 2:7. A representative mineral is hemimorphite, that is Zn4Si2O7. Such silicates are known as sorosilicates. In the sorosilicates, two SiO4 tetrahedral are linked by sharing one oxygen, thereby forming discrete, that is Si2O7 to the power of 6 groups in their structures. A few simple sorosilicates exist as minerals. Structures containing both Si2O7 and independent SiO4 groups also occur, the most important being vesuvionite and minerals of the epidure group. These commonly form edge-sharing linked octahedral chains. These chains in turn form a sheets by binding with isolated SiO4 tetrahedra, while bonds between chains and within sheets are quite strong, that is large coordination spaces that accept the large cations. Then bonds between sheets are weak, leading to the common phenomena of only one, that is because due to the direction of perfect cleavage, SiO4 tetrahedride in combination with Si2O7 units, this tetrahedral forms a discrete composition group in few rather sorosilicates. The composition is Si2O6 to the power of 7. These double tetrahedral units are linked to other similar units, though the bonding with charge balancing cations to the active oxygens of adjacent composite units. Such silicates are known as sorosilicates. Examples: lawsonite, hemimorphite, zoisite and allanite, etc. Then third important classification is ring structures. This is also called as cyclosilicates. In this class, two of the oxygens of each tetrahedron are shared with neighboring tetrahedra, and the angular positions of the tetrahedral are such that closed units of ring-like structures results. Rings of 3 or 4 or 6 tetrahedra are known. The typical examples of each with an Si:0 ratio is 1:13. For example, is bentonite, that is BATI Si3O9 with 3 linked tetrahedra, that is axinite and the beryl. The cyclosilicates are so named because they contain rings of linked SiO4 tetrahedra. The tetrahedra are linked in the same manner as in the single chain inosilicates, and with each SiO4 group sharing 2 oxygens with adjoining tetrahedra on either side, thus giving the same overall formula Si3O3 to the power of 2. However, instead of forming a straight chains, the tetrahedra are joined at angles that result in the formation of rings. The minimum number of tetrahedra required to form a ring is of course 3. A few 3-membered ring minerals are known, the best known being axinite. Several important minerals, examples beryl, cordierite and tourmaline, have 6-membered rings. Then let us go to the chain structures, that is called as inosilicates. The chain structures, that is tetrahedra, are joined together to produce a chains of indefinite extent. There are 2 principal modifications of this structure yielding somewhat different compositions. Single chains in which the Si:0 ratio is 1:3 as characterized by the pyroxenes and pyroxenites. Double chains in which the alternate tetrahedral in 2 parallel single chains are cross linked and the Si:0 ratio is 4:11 as characterized by amphiboles. The chains may be indefinite in extent or generally elongated in the C direction of the crystal and are bounded of each other by the metallic elements. This division of the silicate is known as ionosilicates. The ionosilicates are a subclass in which the SiO4 tetrahedra are linked to form the chains of indefinite extent. There are 2 main types of chain structures. One is single chains in which each tetrahedra is linked to the next by a common oxygen to produce an overall composition SiO3 to the power of 2, and double chains in which the 2 single chains that are side by side are cross linked through alternate tetrahedral to produce an overall composition Si4O11 to the power of 11. Each type is represented by an important group of rock forming minerals. The pyroxenes are single chain structures, the amphiboles are double chain structures. Minerals of the 2 groups have marked similarities in structure and in physical and chemical properties. In each, the chains are aligned with their elongation in the C direction of the containing crystals, and adjacent chains are bonded by ions, mainly calcium, magnesium and iron, that lie between the chains. Furthermore, the unit shells of analogous minerals of the two groups are nearly identical except for doubling of the period in the B direction in the amphiboles. Sheet structures, that is pilosilicates. In sheet structures, 3 oxygen of each tetrahedron are shared with adjacent tetrahedra to form a flat sheets of indefinite extent. In essence, this structure is the double chain iosilicate structure extended indefinitely in 2 directions instead of only one. The linkage, which gives an Si:0 ratio of 2:5, is the fundamental unit in all mica and clay structures. The sheets form a hexagonal planar network that is responsible for the principal characteristic of minerals of this type. Their pronounced pseudo-hexagonal habit and their perfect basal cleavage parallel to the planes of the sheets. This division of the silicate is known as pilosilicates. The basic structural feature of the mineral in this subclass is the presence of SiO4 tetrahedra linked by sharing 3 of the 4 oxygens and thereby forming a sheets with a pseudo-hexagonal network. These sheets are variously referred to as the silica layers or silica sheet, or it may be also called as tetrahedral layer. All of the pilosilicates have a perfect basal cleavage which takes place between the composite layers. Although some of the pilosilicates are stable to rather high temperatures, many of them are formed at ordinary temperatures as the result of sedimentary, diagenetic or weathering processes. It seems that the sheet structures are more readily formed under such conditions than the other silicate types. The pilosilicates represent a further degree of tetrahedral polymerization. The pilosilicates have 2:5 ratio of tetrahedral cations such as silica to oxygen. Some of the most common minerals in this group are the micas, example muscovite. The last classification is 3-dimensional network, that is called as Tac Toe Silicates. In 3-dimensional network, every SiO4 tetrahedron shares all of its corners with other tetrahedral, giving a 3-dimensional network in which the SiO ratio is 1:2. The forms of silica, quartz, tridymite, cristobalite have this arrangement. In SiO2, the positive and negative charges balances. In most of the silicates of this type, the silicon is partly replaced by aluminum. So, the composition is SiAlO2, and the substitution of Al plus 3 or Si4 plus requires additional positive ion to restore a electrical neutrality, that is example is nepheline. The feldspars and the zeolites are also examples of this division of the silicates, which is known as Tac Toe Silicates. The Tac Toe Silicates include some of the most important rock forming minerals. The simplest is quartz, that is SiO2 in composition and oxide. It is included here because its structure consists of a framework of SiO4 tetrahedra with oxygen linked to silicon atoms in a neighboring tetrahedrons. Except for quartz and its polymorphs, all the minerals in this subclass are aluminosilicates. In order to produce a net negative charge on the framework, some of the SiO4 is replaced by Al plus 3. Up to half the SiO4 may be replaced by Al plus 3. The most common Si is to Al ratio are 1:1 and 3:1, which corresponds to the formula units of the type Al SiO4 to the power of 1 and Al Si3O8 to the power of 1 respectively. All the Tac Toe Silicates are colorless, white or pale gray when free from inclusions. They also have rather low densities as a result of the comparatively open nature of the Tac Toe Silicate structures. Their hardness are rather uniform, about 4 to 6. On the whole, the Tac Toe Silicates form a remarkably homogeneous subclass with many similarities in composition and properties common to all minerals within it. Example: silica group, feldspars and zeolite groups are some of the most common framework silicates. The silica group, that is SiO2, occurs in nature as quartz, tridymite, cristobalite, coesite, etc. Of these, quartz is very common. Tridymite and cristobalite are widely distributed, particularly in volcanic rocks. In addition, there is a natural hydrated silica, that is Si2 NH2O opal, which is relatively common and widespread. Feldspars groups are the most abundant of all minerals. Although they are closely related in form and physical properties, they fall in two subgroups. One is the potassium and barium feldspars, which are monoclinic in symmetry, and the second one is the sodium and calcium feldspars, that is plagioclase, which are definitely triclinic. The zeolite groups comprise a group of Tac Toe Silicates minerals that are of special interest because they can lose a part of all their water without a change of crystal structure. They can absorb other compounds in place of the removed water. They are also capable of undergoing cation exchange. They form a well defined group of species that are closely related to one another in composition, in condition of formation and mode of occurrence. Based on these basic structural units, we can construct a general structural chemical formula for the silicates. We often find it convenient to use a general formula that fits all species within a given group. One is the W, that is the large cations having coordination number greater than 6, principally calcium, sodium and potassium. X is equal to medium sized bivalent cations in 6-fold coordinations, principally magnesium, iron, etc. Y is equal to medium sized trivalent and quadrivalent cations in 6-fold coordinations. This includes aluminum, iron, titanium, etc. Z is equal to small cations in 4 coordinations, principally silica, commonly replaced by aluminum. The aluminum silicate group of minerals can be considered to include their 3 polymorphs of Al2SiO5, that is andalusite, sillimanite and kyanite, and even topaz, and also a staurolite. Stability relationships of the minerals of this group have been submitted to experimental investigations by several geochemists. Kyanite is much denser than the other andalusite and sillimanite, and hence its formation is favored by high pressures. Sillimanite is characteristic of high grade metamorphic rocks, and hence its formation appears to be favored by high temperatures. Andalusite is commonly a product of the moderately high temperature metamorphism of argillaceous rocks. Mullite is found in a few localities as a mineral where aluminum rich rocks have been subjected to extremely high temperatures, such as where fragments of shale have been picked up by a lava flow. Mullite is used in industry as a refractory, for which the purpose it is made by heating kyanite or andalusite. On heating to 1300 degrees centigrade, kyanite, sillimanite, andalusite and topaz decompose into mullite, that is Al6, Si2, O13 and a silica rich glass. Silicates includes about 1/3 of all mineral species. Silicates are compounds containing anionic and silicon compounds. This is one of the earliest classifications which occur before the formations of a silicon tetrahedra. Structural classification is based on phase sharing, edge sharing and corner sharing. A number of primary silicates crystallize in the nesosilicates mode. Sheet structures members have a platy or flaky habit with one very prominent cleavage. Minerals are generally soft, low specific gravity and may even be flexible. These are similar to the framework silicates in that the ratio of cations in the tetrahedral side, that is silica to oxygen, is 1:2. The high concentration of strongly linked bonds yield relatively dense minerals that are quite hard. Quartz and feldspars are some of the most common framework silicates. The ratio of Si to O ratio is 1:2. Silicate structures helps in understanding the reasons for some of the properties of minerals.